Okay, hi there internet people. This is perhaps one of my most favourite lectures that I ever used to give when I was working as a lecturer, and it's really important to me because the content of this lecture will explain to you why it is that, for example, most of these diets that they suggest out there that will be alkalinizing and therefore healthy for you and better for you and stuff are actually a load of nonsense in terms of the underpinning logic behind them. I'm not here to tell you that some of the foods that they suggest you eat on such diets are necessarily not good for you. What I'm saying is the whole idea behind what they're trying to sell you is a load of nonsense, i.e. that eating different kinds of foods will have a meaningful effect on the acidity control in your body. So what I thought I'd do today is go through what really does control the acidity in your body, how that really does work, and from there we will be able to have a much better understanding of how these things work in the real world, and as I say, why such things are loads of nonsense that you see them advertised everywhere all over the web. So the learning outcomes. Basically, we're going to describe what an equilibrium is, and obviously, as you can see there, it's two parallel but opposite and antagonistic, if you like, half reactions which balance each other out. We're going to talk about a chap called Le Chatelier and a principle that he came up with that describes what happens to an equilibrium when we try and shove it one way or another, try and mess around with it basically. We're going to talk about what is auto-ionization in pure water, and how that leads to a stable pH value which depends entirely on temperature. We're also going to explain how pure water interacts with carbon dioxide gas, which is floating around in the atmosphere all around us, and how that has an effect on the pH of so-called pure water. Indeed, that concept, just for a bit of a spoiler, is going to show us how, in fact, any water that is so-called pure, that's exposed to the air, in fact, is no longer pure. We're going to describe how organic acids interact in water, which also have an effect on the pH. We're going to describe how various different ions in the water affect the pH as well. This is one that most scientists get entirely wrong. This is one that is overlooked almost entirely, both in the literature and in the lecture theatre. Hello, dog. Nice to see you. Yeah, and this is one that I'm going to put straight today because this is one that, yeah, we need to understand this because if we don't understand this, we do not understand how pH control works. So stay tuned in. It's well worth staying tuned in for that. And we're going to talk about a thing called the Law of Electroneutrality. Now, again, as a bit of a spoiler, let me clarify this one right now. It says the Law of Electroneutrality, not the theory of electroneutrality, not the maybe this is a good idea of electroneutrality. This is a law. This is a law of physics, and we need to understand that in any fluid pool anywhere in the universe at all times, the net charge of all positive and negative ions in that fluid solution is necessarily always at all times zero, and that has a big impact on pH control. By the end of the lecture you'll understand how that's so as well. So at the end we'll thereby be able to summarize the laws of pH control, and in fact what we'll be able to do is work out through this lecture today that there are actually only 4 different control levers on the pH in any fluid pool anywhere in your body, be that inside a cell, in your blood, the extracellular fluid, cerebrospinal fluid, doesn't matter what it is. If it's a solution based on water, there are 4 and only 4 variables that you can change that will have any effect on the pH. And we'll talk about what those are in the course of this lecture. So, without further ado, let's crack on. What is an equilibrium? Okay, an equilibrium basically is a chemical reaction that occurs left to right and right to left simultaneously. It's a reaction and it's negative, opposite, antagonistic reverse reaction. So when we talk about reactions in chemistry, we're talking really about an effective collision between species A and species B, leading to the production of species C and species D. So basically the reverse reaction would be an effective collision of species C and species D, which leads to the production of A and B. Each molecule pairing, if you like, of species A and species B in the fluid solution has a likelihood, a probability of colliding effectively to form C plus D per unit time. Now that likelihood is determined by the concentration of the species A, the concentration of the species B, and the temperature of that fluid pool. Now why is the fluid temperature important? Well, that's the thing that determines the likelihood that a collision is going to be effective, because heat is the form of energy that the molecules are carrying, which means that they kind of vibrate more, and so when they whack together it's more likely that the electrons, which are more energized if you like, will interact with each other in such a way as to form these chemical reactions and allow them to occur. That all being said, when you've got a C and a D in your solution, it also has a likelihood of colliding effectively to form A and B again. In other words, back to where we started. So that likelihood is determined by the concentration of species C, the concentration of species D, and that temperature. Okay. So let's say A plus B goes to form C plus D is an endothermic reaction, which means it absorbs heat energy. To get this thing to occur, we've got to put heat in. It absorbs that heat energy to activate it, and in so doing it actually lowers the temperature of the whole solution. You've got C plus D out of that reaction, and the reaction C plus D goes to reform A plus B again is necessarily an exothermic reaction in this case. It then releases heat energy. So what are we saying? The fluid pool resists changes in temperature because while one reaction is cooling the solution down, the reverse reaction is heating it back up again. So it's kind of, there's a balance, and also because of the probabilities of those reactions occurring, we get a balance in the actual concentrations of A and B and C and D, even though there's constant flux through that reaction system both backwards and forwards. So what we're saying is that the temperature of the solution is the first energy control lever for the system. A plus B goes to form C plus D, and at the same time C plus D goes back to form A plus B. Okay, so the temperature controls the pH of a fluid solution. If you externally cool that solution down, draw heat out of that solution somehow, the right to left reaction is favoured and the equilibrium balance will kind of move to the left, for want of a better term. If you heat the solution up externally, stick a flame under it, then obviously the reverse reaction is favoured and the equilibrium balances will move to the right. Okay? So, how does this equilibrium establish itself? Okay, we're talking about the odds. So let's say the odds of species A plus B going to form species C plus D are 1 in 100 per A plus B pair per unit time, just for one of other numbers. And let's say the odds of a C plus D goes to form an A plus B reaction, the reverse reaction, are 1 in 10 per C plus D pair per unit time. Okay, so let's say we begin with a concentration of A and a concentration of B, which are both 100 units per volume. Okay, and let's say we begin with a concentration of C and a concentration of D, which are each 9 units per volume. Purely arbitrary, I've made these up because it works really well, but watch what happens. Okay, given that we have A plus B goes to form C plus D is a 1 in 100 odds, and we have a concentration of 100 of each of A and B, after T equals 1, our unit time, then A and B both lower to become 99 each, because there's a 1 in 100 chance that each one of them will do it within that unit time. Okay. However, in the same unit time, because of the odds of the C plus D reaction occurring, the C plus D would each be 9 plus 1 equals 10. In other words, that's what's happened after the A plus B goes to C plus D reaction. Okay. So given that the C plus D equals A plus C plus D goes to the A plus B equals 1 in 10 odds, okay, we have A plus B, which is 99 plus 1 is 100 again, and the C plus D is 10 minus 1 is 9 again. In other words, we still have 100 of each of A and B and 9 of each of C and D. In other words, the reactions are occurring all the time constantly, but the actual concentrations are not changing. We have an equilibrium. Okay, I hope that was reasonably digestible. Moving on from there, let's talk about Le Chatelier. Okay, basically, in a nutshell, obviously Le Chatelier used much more technical language, and I think he was French, probably French rather than English, but in any case, the take-home message is if an equilibrium is formed, it will persist even if you try and disturb it. Think about an equilibrium balance as a heavy pendulum on a solid arm hanging vertically in gravity on an A-frame. If you try and shove that, gravity will cause it to shove back and resist you. Okay? So depending on the weight of that ball, that would determine on the resistance of that particular equilibrium, if you like, to being shoved one way or another. So if there's a change in the concentrations of A or B or C or D, or any kind of partial pressures involved in those concentrations, or volumes, the system concentrations all react to the change that we make in such a way that a new equilibrium balance is established, and that it all happens within really about a millionth of a second. In actual fact, to all intents and purposes, it's instantaneous. The reason that we say about a millionth of a second is because we actually don't have the technology to measure it any more rapidly than that. So basically what occurs is we say, okay, well, it's within that period, but let's just say it's instantaneous. Okay, so the equilibrium balances of A and B and C and D all change very slightly, but not as much as you would expect given the shove on the system that you gave. So in effect, what we're saying is the equilibrium will resist attempts to perturb it or to shove it off its balance, if you like. What the principle says is that any equilibrium has a massive power to buffer change. Okay, it resists very, very strongly, so that's the thing to keep in mind. And that kind of leads us to a discussion on this thing that they call the equilibrium constant. So let's move on to that. Okay, equilibrium constant, it's denoted K with a C subscript, and basically it equals the products divided by the reactants if you view the equation from left to right. So basically, in effect, what you're looking at is Kc, the equilibrium constant, equals the concentration of C times the concentration of D divided by the concentration of A times the concentration of B. Whew. So in the theoretical example that we just spoke about, the Kc is 9 times 9 divided by 100 times 100, or 81 divided by 10,000, or the Kc value of the ABCD reaction we spoke about before, given those odds of those reactants reacting with each other, the Kc value would be 0.0081. Now, each equilibrium is given a Kc value. It's called a constant. Now, the thing about a constant is, the key word here, the giveaway term here, I guess, is constant. Constant means unchanging. It means this is a value that does not change. Keep that in mind. Okay. Just by way of to explain some of the notation, as I said, K denotes the equilibrium constant and the subscript C denotes the equilibrium of the concentrations of species. So yep, that's what that's about. Okay. Now, when you try to perturb a equilibrium, there's a thing I like to teach students, which is a thing called the SOOS rule, which tells you what will happen to the concentration of A, B, C, and D, depending on what you do to what. And SOOS means on the same side as the thing that you change, the other reactant will have the opposite response to what you did, and on the opposite side, both reactants will react in the same way as what you did. So, for example, what happens if I increase the concentration of species A? Okay, so what happens is, in actual fact, A remains fairly constant. That's what the Le Chatelier's principle is about. It resists the change. Okay, and the reason that happens is because the extra A that you put in reacts with the B, thus dragging the concentration of B down, because that then flows through to the right and causes the concentration of C and D to both go up. So put up A, same, opposite, B goes down, opposite, same, C and D both go up. Cool? So that's basically what that says there. So that's how it's very, very difficult to change the concentration of species A by adding A or by removing A. If you removed A, then C and D would flow through to the left, cause B to go up, but A would remain fairly constant. Okay, so I hope that was kind of at least as clear as mud. Okay, so given that A plus B goes to C plus D is endothermic in this case, what would happen to the value of Kc, which is C, the concentration of C times the concentration of D over the concentration of A times the concentration of B, if, number one, we cool that solution down, or number two, we heat that solution up. Okay, well, if the temperature is lowered, A and B increase and C and D decrease, i.e. the value of the constant Kc reduces. Huh? I thought we said it was a constant. Constant meaning unchanging. No, that's BS. That constant is not a constant, it's a variable. It's just not an independently moderatable variable. We can't change it directly. We can only change it by changing the concentration of species present in that solution. Okay? So the whole term equilibrium constant is an absolute nonsense. It's a variable and it's a dependent variable. Okay? By the same token, if we raise the temperature of the solution, A and B are going to decrease, and also C and D are going to, so you get the same sort of thing going on there. Okay? So what actually happens is the constant Kc is going to increase. Okay. So let's put all this together a little bit and talk a little bit how that applies to water. Okay, so we're going to talk about auto-ionization of water. Okay, so remember that an equilibrium is a species A plus a species B forming a reaction with species C and species D, and the reverse reaction occurring back the other way. Okay. So in this case, what we're talking about is water reacting with water to form a thing called a hydronium ion, H3O+, and a hydroxide ion, a thing called an OH-. Okay, how does that work? Two H2Os floating around in solution, bang into each other. A proton is transferred between one of those water molecules gives up a proton to the other one, basically, and so that's how you get the H3O plus OH-. Now there's an idea that chemists like to talk about, and it's called the conservation of mass, whereby what they say is everything on the left and everything on the right of the reaction will have to add up, it's stoichiometrically, and mass is conserved and all that. Okay, Nonsense. Mass is not conserved. That is absolutely not supported by physics whatsoever. Energy is conserved, but not mass. In any case, chemists, what they will often do, in this case, is they will cancel out one of the H2O's on the left-hand side of that reaction and on the right-hand side of that reaction. So what they get is H2O forms a reaction with H plus OH minus. Now, this has always pissed me off. Okay, the reason for it is that little notation at the bottom of the screen there would seem to suggest that in water there are protons floating around, H plus, and hydroxide ions, OH minus. That is nonsense. That never occurs in water at physiological temperatures whatsoever. It's H3O plus OH minus, and the reactants with 2 molecules of H2O. Okay? I've always been one for calling a spade and not confusing people. I think that bottom notation is very confusing. I think it's wrong. It annoys me. But anyway, that's what they've done. Okay. So, the concentration of water in water is 55.56 moles per litre, which assumes a molecular weight of water is 18 grams per mole, give or take. Depends on how much the water is heavy and how much of it's light. Different isotopes of the different things involved. Don't worry about that. It's near enough. Okay. It also assumes that the density of the water is 1,000 grams per litre, or 1 kilogram of water equals 1 litre, which is pretty close under most circumstances. Okay. The concentration of hydronium ions, otherwise usually referred to as H+, in pure water at 25 degrees C is 10 to the power minus 7 moles per litre. Okay. Now, why has the temperature got anything to do with that? Remember how we said that the temperature depends or determines how effective the reactions are, and so therefore heating it up will mean you've got more reactants, and cooling it down will mean you've got less. Okay. Given also that in pure water all you've got is H2O and H2O, you've got a small amount of H3O plus, 10 to the minus 7 moles per litre. You've got the exact same amount of OH minus, of course, because when you go back, that's all there is. Okay? So, the equilibrium constant of that reaction works out to 10 to the minus 14 divided by 55.56. So you get this ridiculously small number. So when I gave you that number before that just had a couple of zeros, and it was just a contrived example. Obviously in the real world with things like hydronium ions and hydroxide ions in pure water, there aren't very many of them. Okay? So we talk about this thing called pH 7 of pure water. Pure water has a pH of 7. Okay, well, if pure water had a pH of 7, what percentage of the molecules would be ionized into hydronium ions and hydroxide ions? Okay. Well, it would be 10.7 divided by 55.56, which was the concentration of water in water, which gives us 0. All those zeros, 18. Okay, we need to multiply that by 100 to make it a percentage. So what we've got is 0.0000018% of all the water molecules in pure water at 25 degrees C are ionized. What does that mean? It means 18 molecules are ionized out of every 10 billion. Okay, or 10,000 million if you like. Okay. Which, if you do the math, works out to 1 molecule is ionized in every 555,555,556, give or take. Okay, so at pH 7 there are basically almost no ions. It's all water pretty much. Okay. Just a quick note before we move on. Sometimes people talk about KEQ and KC sort of interchangeably. There's some notes there for you to read through at your own time, basically on what that is. There are slight differences to all intents and purposes. We don't need to worry about them at this level. Okay. So, water has a dissociation constant, okay, which is denoted by Kw, and it is the concentration of H₃O plus times the concentration of OH minus, which at 25 degrees C, we spoke about before, is 10 to the minus 14 is the number, okay, which is 0, 0, 0, lots and lots and lots of zeros. Okay, so out of that, what we can ascertain mathematically is that the concentration of H₃O plus is 10 to the minus 7 moles per litre, and the concentration of hydronium ions is 10 to the minus 7 moles per litre. Okay, there's a thing called a pK scale, which basically is the negative logarithm of the original number. So 10 to the minus 7, the p-value for 10 to the minus 7 is 7. So when you hear about pH, the acidity is on a pH scale, that's what the pH means. Okay, it means that a p-value of 7 for the hydronium ion in this case, or pH, is 10 to the minus 7, or as we spoke about, 18 molecules per 10,000 million. Okay. Now, given what we spoke about before about cooling it down changes the value of the K value, and heating it up also changes the K value, I can actually give you some different values here. So when I said that it's pH 7 at 25 degrees C, that is not true if you heat that water up, for example, to 50 degrees C. Pure water has a pH of 7, I was once told by an arrogant old external examiner who was being gruff with me and saying, what are you talking about? Okay, yes, Charlie Brown, that's absolutely true, if and only if that water is at 25 degrees Celsius. If you heat it up to 50, that same pure water with nothing else in it but water molecules will actually have a pH of 6.63. In other words, the lower the P number, the higher the concentration of H plus, H₃O plus, the more acidic it is. So lower number, more acid. Okay, so you heat water up, pure water, and it becomes more acid. You cool it down, let's say to just above 0 degrees C, then it has a pH of around 7.47. It becomes less acid. We haven't changed the chemical concentration at all. All we've done is change the temperature. That's interesting. Okay, so out of all of that, what we're basically saying is that there are four, as we spoke about at the beginning, there are four and only four ways to change the pH of a solution based on water. One of those ways is to change the temperature of the water. Okay, so we've spoken about that. I think I've done that one to death. You change the temperature, you change the pH. Cool. Second way that we can change the pH of a water-based solution, and this happens whether we like it or not actually, is the CO₂ interaction. Okay. What I want you to imagine is a 1 litre sphere or cube, it doesn't matter, of water, which is magically floating in space in front of us. It's not subject to gravity, it's not subject to contact with any other substance. It's just floating there in space. If it was 25 degrees C in that case, then it would have a pH of 7. Cool. Alright. In the air, the atmosphere all around us, there is an amount, a small amount, a very small amount, of carbon dioxide gas. Carbon dioxide gas reacts with water. So any time you have some water which at any time is subjected to contact with the atmosphere whatsoever, it will absorb carbon dioxide out of the atmosphere into it, for example. Okay. So pure water has a given propensity to act as a solvent for carbon dioxide. In other words, carbon dioxide gas dissolves into it and becomes carbon dioxide in the liquid form. The amount of carbon dioxide that will be dissolved in the pure water depends on the temperature. Okay, it has a K value. That K value is temperature dependent. So the temperature is very key here. And also, it depends on the pressure of the carbon dioxide gas that is driving it into that water. So in the atmosphere, very, very low pressure. Inside a working cell in your body that's producing a whole bunch of carbon dioxide, much, much higher. Keep that in mind. So, again, at 25 degrees C and at a barometric pressure of 760 millimeters of mercury for the air, 1 litre of water will dissolve approximately 0.001 moles of carbon dioxide into it. That will form a substance called carbonic acid. Carbonic acid forms via the interaction of CO₂ plus H₂O. And of course the reverse reaction again, has a propensity to occur, and so therefore it has a K value, and it's given to you there. 1.7 times 10 to the minus 3 is the K value for that reaction. So basically what that means is if you've got 0.001 moles of carbon dioxide dissolved in your 1 litre of water, then it's going to form 0.0000017 moles of carbonic acid. So what that means is pure water opened to the atmosphere is not pure and will not have a pH of 7, even if it is at 25 degrees C, because the carbon dioxide dissolves into the water depending on the temperature of that water and changes the pH of that water by putting carbonic acid into it. Okay, so the behaviour of any acid in water we know about, and we'll just denote the acid as HA. In this case we're talking about carbonic acid, but it's a true statement for any acid. Mix it with water and you get H3O plus and A minus. It has a Ka value. There you go, there's the math if you like. Or another way of describing the same math is like that. Hate it, don't do it, it's wrong, a spade's a spade, so let's do it that way. Okay. And as again, as I spoke about before, the P value is just the negative log value, and so it gives you a number that supposedly is easier to understand, but it's an inverse scale. So when you're talking about acidity, the lower the P value, the higher the acidity. The higher the P value, the lower the acidity. Crazy, but there you go. Okay. So therefore, the specific behaviour of carbonic acid in water, H₂CO₃ plus H₂O forms H3O plus HCO3 minus. Obviously the reverse reaction occurs as well. So the Ka of that at 25 degrees C is 4.2 times 10 to the negative 7, which gives you a pK value of 6.38 at 25 degrees C. Don't forget though that the human body is at 37 degrees C, so that actually changes that effective constant value to 6.10. Okay? So, if we have a concentration of carbonic acid in our water, 0.0000017 moles per litre, that will dissociate, as you can see above, into some bicarbonate. So there'll be some bicarbonate in the water as well. How do we work out how much there is? Well, first of all, we need to know what the pH is. So we just do a little bit of mathematical trickery here. Don't stress yourself with it. Just believe me, this is how it works. So in this case, with that concentration of carbonic acid with its known constant, that will give us a pH value of 6.07 in that solution. So what are we saying so far? We're saying that pure water at 25 degrees C has a pH of 7, But in the human body, the temperature is 37 degrees C, so that means it's not 7, it's below 7, it's 6 point something something, whatever the number was I showed you before. Okay. And the water is going to dissolve some carbon dioxide into it. Let's say the only thing that was dissolving into it was atmospheric carbon dioxide. Even that would pull the pH down lower, make it more acidic. So basically, just by being, the water in our body is steadily becoming more and more acidic. And yet, our body temperature is 37 degrees Celsius for a reason. And there's carbon dioxide in our bodies for a reason. Interesting. Anywho, there's a thing called the Henderson-Hasselbalch Equation, which we can use to therefore work out what that concentration of bicarbonate is. There it is, the math, if you like that sort of thing. Hello once again, dog, nice to see you. Okay, there's also an equation variant that's useful for clinicians, because as I was talking about, the carbon dioxide is much more concentrated inside the cells of your body and in the blood and in the interstitial fluids of your body than it is in the atmosphere. And so the math that they use to work that out is all there, so we can actually work out these different concentrations. Don't stress yourself with that. That was just there for my students in the past who needed to do that kind of stuff for their exams, but you don't need to worry about it. What we're saying basically is CO2 dissolves into pure water and forms carbonic acid. Carbonic acid reacts reversibly with water to form magic hydronium ions plus bicarbonate ions. So the concentration of H3O goes up some. Same, opposite, opposite, same, which means the concentration of OH minus goes down some, and H2O concentration goes up some, but not really perceptibly because of its huge magnitude compared with the very, very small magnitudes of the two ionic species. So basically, carbon dioxide entering the solution reduces the pH still further than it was already reduced by being heated above 25 degrees C. So thus CO2 leaving the solution increases the pH. In other words, when you breathe out carbon dioxide gas, that's a way of controlling where the pH is at. And yet there's still enough carbon dioxide in your tissues and in your fluids and in your blood to keep the pH value much, much lower than it would be if it was just pure water. Isn't that interesting? The other interesting part of it, obviously, is what we've been alluding to, basically, is the fact that carbon dioxide does dissolve into water. It gives us a way of uncoupling the concentration of hydronium ions from hydroxide ions, because otherwise if it was just water, they would have to be equal all the time, because that's all there is. You add the carbon dioxide, that adds the H2O, that's what throws those things out of kilter with each other. So, yep, I hope that was accessible. Don't forget that the amount of carbon dioxide gas which will dissolve in water depends on the driving pressure of that carbon dioxide gas, the temperature of the carbon dioxide gas itself, the temperature of the water, which obviously in the body are both 37 degrees C, and the pressure and density of the water, which doesn't really change very much from a day-to-day basis to all intents and purposes. But the relevance of that is like for very extreme environments like zero air pressure or very low air pressure or very high underwater pressures with diving, or those kind of things. So also don't forget that cell fluids are subject to carbon dioxide partial pressures as produced by the metabolism rather than as just exerted directly by the atmosphere. So the rate at which carbon dioxide enters those fluids is changeable upward and downward on a second by second basis rather than just how much carbon dioxide is in the atmosphere. 0.000395, blah blah blah. Yeah. Okay, so PO2 in the PO2 meaning the partial pressure of the carbon dioxide gas in the cells and the blood is much, much higher than in the atmosphere. That's how breathing out gets it out of your body, because basically it goes down its concentration gradient in the alveoli in your lungs. Okay, So basically what we've said, is that your body fluids being warmer than 25 degrees C makes them more acidic, and also the fact that carbon dioxide as air makes them even more acidic again. So what we'd be saying is that being very, very acidic is very good, it's the natural design, that's how things are, and that would be true if that was all that was involved, but unfortunately there's always more. So yep, it's a bit more complex. Let's finish off and get the full story then, shall we? Okay, weakly dissociated acid anions. Basically, your whole body is made up of proteins. The cell walls have got proteins in them. There are proteins in the fluids themselves, in the biological fluids. Albumin and globulins are the most sort of prevalent. But don't forget all the proteins embedded in the cell walls themselves and in the walls of your vasculature and all that sort of. They all have a bunch of electronegative charges on the surfaces of those different proteins, depending on what amino acids are there and what sort of thing. But they all have multiple, hundreds and hundreds, tens of thousands, sometimes millions even, of these negative charges all over the surfaces of their of the structures of those proteins, basically. And so they effectively add a negative charge into the fluid pool, which is modelled as an effective charge in milliequivalents, and we just call that variable the ATOT, or the total A charge, or A negative charge, if you like. Okay, and the value of that charge is given as the effective concentration of all those acids plus their anions, basically. It has an effective K value overall. Each individual different protein has a different K value, but they all mix together and add up, so you get this overall value, I guess. So what we're saying now is, okay, so being hotter than 25 degrees C makes us acid. Having carbon dioxide in our fluids makes us still more acid again. And the fact that we're made of proteins, oh god, that makes us even more acid. But hang on, I thought being acid was bad. That's interesting. Well, hang on. We know that the blood has a pH of 7.2 to 7.4, and the acidity of a working, muscle cell is only slightly more acidic than that, at around about 6.8. So what on earth is going on here? I've just been telling you all the reasons why we're acid, but the observation doesn't match that. We are not acid. We have a pH of 7.2 in the blood to 7.4 and around about 6.8 in a very heavily working muscle cell. Must be something going on here that we don't really understand. Well, there is. There's another variable called the strong ionic difference in the fluid pool. So whether it's your blood, whether it's the fluid inside one of your cells, whether it's interstitial fluid between your cells, whether it's cerebrospinal fluid, doesn't matter. Any fluid pool anywhere in the universe at all times must add up all the positive and negative charges, all the different ions that are dissociated, all the different proteins, all the H plus and OH minus, and all the carbonic acid system ions, all add up to 0 at all times, always. It cannot ever have any other value. It must be 0. It's called the Law of Electroneutrality. Okay? Basically what would happen if you had a charge difference between pluses and minuses in any given fluid pool, that would result in a spontaneous and instantaneous electrical discharge through that fluid pool, and it would be a massive discharge for a very, very small concentration change. In other words, basically the person would explode. You'd explode. But that doesn't happen. Okay. Why doesn't it happen? It doesn't happen because anytime you try and change that value, all the K values, which are so-called constants, change. And they change in such a way as that everything shifts around, Le Chatelier's principle, in order to resist the change that you're trying to make to maintain a net electrochemical charge of 0. So here is the practical upshot of all of that. There are no fatal electrical discharges, spontaneous discharges through fluid pools. Okay, you don't just explode. Okay, if you try and add an unnegated positive charge in any form whatsoever, then the H₃O concentration will drop. In other words, you will become less acid. If you add an unnegated negative charge, then the concentration of H₃O plus will go up. In other words, you will become more acidic. This is neither good nor bad, because the pH of your body overall is controlled within a very, very narrow band at all times. So this happens because it's supposed to happen. The acidity is supposed to go up and down in your body. It does it so that you don't explode. Okay? So what is the SID, and why has it got a plus in front of it? It is the net strong ionic difference in the biological water-based solutions. It always has a positive charge. Why does it always have a positive charge? Because your body maintains concentrations of ions against their concentration gradients by pumping them in such a way that it always does have a very strong positive charge. Why does it have a very strong positive charge? Because being hotter than 25 degrees C makes you acidic. Having carbon dioxide dissolved in your blood makes you acidic. Being made of protein makes you acidic. So we have to counteract that by putting in a bunch of positive charge to drive that H₃O plus back down to the physiological range, yeah? So that's basically how that all occurs. So let's have a quick look at some summary relationships on how all of that works. This diagram comes from an article that I published, oh god, I think it was about 2008. Anybody that's really interested can contact me and I'll give you the reference for it. But basically this talks about these relationships. What it says basically is that water interacts with itself according to the constant Kw, and that produces H plus OH minus. Bloody doesn't. It produces H₃O plus OH minus. Let's get over it. Okay. So down the bottom left hand corner we can see that if we increase the temperature, that changes the value of Kw, a thing called S, a thing called K1, a thing called K2, a thing called K3, a thing called Kc, and a thing called Kha, among others, in such a way that if we heat it up, we become more acidic. Again, if we cool it down, opposite, we become less acidic, because Le Chatelier's principle means everything on all three other arms all interact in such a way as to basically either flow H plus in or draw H plus out of the middle of this chart, if you like. And so body temperature remains pretty stable, only changes a very little bit. So that's not really a way that physiologically we can get it controlling pH, or the way the body gets at it. So that's, while it's very important to understand how it all works, that's not something the body uses to control its pH particularly. Okay, so ATOT, the total net concentration of all the proteins and things that are both floating around in your fluids and also making up the body structures themselves. That can change up and down. Sure, your body can synthesize more proteins, or your body can break those proteins down. And so that's one way that your body can control the net relative pH of your body fluids and the different pools, either inside a cell or intercellular interstitial fluids, cerebrospinal fluid, blood fluid, whatever it is. The protein concentration in that fluid can be changed in such a way as to maintain a pH value in that fluid where it needs to be, and indeed it can maintain gradients between the pHs of fluids that are separated by semi-permeable membranes. So okay, we can make more protein, we can break protein down. Great, that's the way your body can get it doing that. The partial pressure of carbon dioxide. Okay, well, we can exercise more intensely and produce more carbon dioxide, which of course will cause more carbon dioxide to be dissolved in the blood, even though our breathing rate goes up and our heart rate goes up to get our blood pumping around and exchange more blood through the lungs per unit time and get more carbon dioxide out through its concentration gradient, there is still more carbon dioxide that remains in an equilibrium balance dissolved in that fluid. And so exercising is one way that we can change the pH of our body. Hyperventilating without exercising obviously means we get more carbon dioxide. It's called blowing carbon dioxide off, and that will change the pH of our blood, and so that's another way of changing the pH. Our base metabolic rate can go up or down. That can change the pH in our blood. Or we can change the effective SID value, and the way that we can do that is to change the values of the dissolved ions in our solutions. Any ions whatsoever will do this, and there are literally thousands and thousands of different species of ions in your blood and in your different fluids and things. But there are really only 4 that actually have a significant, meaningful effect on your pH, because those 4 and only those 4 have concentrations that are so much higher than everything else that it just swamps everything else. It doesn't matter. So really, you change the sodium content, the potassium content, or the chloride content of your fluids, or the lactate concentration. How do we change lactate concentration? That happens when glycolysis goes up. Most notably, that goes up. The most obvious way is exercise. You exercise intensely, you produce a lot of lactate ions, that drags your pH down. Which a lot of exercise physiologists will say, and that's one of the reasons why our muscles get tired, because they become acidic. Absolute nonsense. It happens because it's supposed to happen, it's indicated, and it actually supports the performance of working muscles. That's for another day though, that's a completely different lecture. So how do we change sodium, chloride and potassium in our system? Well, the kidneys will do that for us by filtering it in or out, basically. So let's get to this discussion about let's eat some alkalinizing foods. Well, no. Okay, anytime you add sodium, chloride or potassium into your system or remove it from your system, that will change the pH. Your kidneys do a great job, unless you are ill, of looking after that. There is nothing that's going to happen from eating a diet one way or another that's going to meaningfully change the pH of anything except your urine, because it's supposed to. That's the outlet for all these so-called ashes, which just refers to ions left behind when you metabolize your food. So basically that's that one. Let's just talk quickly about the summary laws before finishing up, and I'll let you get on with the rest of your day, whatever you're doing. Okay, here we go. 1. The net electrochemical charge of any and all fluid pools anytime, anywhere in the universe, in all places, at all times, is 0, always, can't be anything else, ever. Cool. pH is dependent variable. You cannot independently moderate the pH by adding H+ or by removing H+. The same goes for pOH. It's a dependent variable, it's not an independent variable. You can't change it or moderate it independently. K values that control all the different dissociations and rates of different reactions and things are called constants in the textbooks. The literature will call them constants. Most scientists will call them constants. They are not constant. They are also variables. They're dependent variables. They change. They can be changed. I've shown how that happens today. Basically, most of what's taught in most institutions around the world is absolute nonsense. Okay. Therefore, there are 4 and only 4 independent variables that we, or the body, can use to change the pH of any of the fluids in that body, and they are: 1. Change the temperature of that fluid. Body doesn't really do that unless you're sick. It'll get a bit warmer. It gets warmer to kill off the invading bugs. That'll make you a bit more acidic, but so what? You're still within the physiological range. Unless you are critically ill, it's not an issue. Okay. We can blow off some CO2. We can produce some more CO2. That'll change the pH, again, within a physiological range, which is tightly controlled at all times, unless you are critically ill. And the 4th way that we can change the pH is we can change the concentration of any one of 4 ions in those fluids, those being lactate. Most usually we change that by exercising. Sometimes it goes up when we're critically ill as well. It can go up in very advanced cancers because of the large rate of glycolysis there, but mostly that just goes up when you exercise and goes back down when it's basically goes back through the Cori cycle, and it's just basically gluconeogenesis. New glucose is made out of it, and some of it gets used up in other ways, oxidized through the whole system, but mostly that's what happens to it. It just goes back to becoming sugar again. And the other three ions that we can change the concentration of are sodium, chloride, and potassium. That's it. Okay, that is how pH is controlled within the human body. Like I said before, the pH of the blood is 6.8 to 7.2. The difference between those in terms of how many hydrogen ions, or hydronium ions if you like, are floating around in the blood, the difference between 6.8 and 7.2 is 2/3 of 5/8 of 7/9 of bugger all. The range is tight. It's very, very tight. It's tight on purpose. This whole idea that we need to control our pH externally is absolute and utter nonsense. Your body does it massively effectively all by itself. It does not need any help from you whatsoever, and certainly not by changing your diet, which will not work anyway. Thanks very much. I hope you enjoyed the lecture. That's the kind of lecture that I'm going to be giving on here. You can have this one for free. Please do become a patron. Please do join. Please support what I'm doing. I'm trying to get the actual facts out there to the people, instead of what's basically taught in these institutions, which, as I've shown to you today, is absolute nonsense. Anybody that wants me to back up any of the assertions that I've made in this lecture with some literature and stuff, please do email me, and I can get those to you. Alright, so have a great day. Enjoy whatever you're doing. Thanks very much.